Hello and welcome to another video. In this video we're going to be doing counting bits. And I will say, even though this is an easy problem, the solution we're going to have is definitely not going to be an easy solution because we are going to focus on the linear time solution here. So essentially you're given an integer n and you want to return an array ants of length n plus 1 such that for each I, array I is the binary representation of 1. So for example, for 2, we want to return what's the binary representation of 0, like how many ones? Well, it's going to be 0, then 1. So the binary representation of 1 is this, so that's going to be, or I guess we can just draw it like this. So we can draw out the binary representations, and then we will draw out the numbers. So for 2, it's going to be 1, 0, right? So here we should have 0 ones, here we should have 1, 1, and here we should have 1, 1. So this should be like the output, essentially. And as you can see, that's what it is here, right? 0, 1, 1. Okay, and then what we want to do here is do this for a bigger number to make this a little bit easier. But actually, I'm just going to go briefly through this quick solution. So basically what we have to do is for every number, we have to get the binary representation. And it's pretty straightforward. Like, let's say we have a number like 3. The way to get the binary representation, the number of ones, is pretty straightforward. You just keep dividing by 2 until it's 0, and you just keep ANDing it with a 1, right? So you would just say like, okay, let me AND my number with a 1, and then if it's a 1, then we'll add 1 to the result, and then we'll divide by 2, right? So if your number's like this, you will AND it with a 1, then you will get 1, you'll put it in the result, and then you're going to want to like shift it essentially, right? So you want to keep shifting until you're out of numbers. So you can just keep shifting right until you're out of numbers. So then what will happen is we'll have 1, 1, we're going to shift that right, so that's going to be 1, then we're going to AND that with a 1, and we're going to get another 1 here. And so essentially you keep doing that, and so that's pretty much all you need to do, is you need to just take your number, you AND it with a 1, you keep shifting until your number is 0, and then that's how many numbers you have. And that's a logarithmic solution because if you have a number like 8, every shift is just dividing it by 2 essentially. So that's like a log solution. You will do 3 shifts to make a number like 8, 0. But we're going to focus on the linear solution. And the way we're going to do this is we're actually going to draw out a bunch of numbers, and we're going to look for patterns. So we're actually going to draw out numbers 0, 1, 2, 3, 4, 5, 6, and 7, and 8. Okay, so we're going to draw the binary representation for all of these, and then we're going to look for patterns. So for 0, and we are going to draw this out in using 4 bits just to make it easier, because we're going to like look down this list essentially. So for 0, it's 0, 0, 0, 0. For 1, it's 0, 0, 0, 1. For 2, it's 0, 0, 1, 0. Then we have 0, 0, 1, 1. 0, 1, 0, 0. 0, 1, 0, 1. 0, 1, 1, 0. 0, 1, 1, 1. And 1, 0, 0, 0. Okay. Now we're going to look for patterns. So one thing to notice is there are a lot of numbers that are similar, right? Like for example, 2 is just 1 shifted to the left 1, right? So like these two numbers, you could see that 2 is just 1 shifted to the left 1. And 3, for example, is just 2 plus a 1, right? And 4 is actually just 2 shifted to the left 1. And 5 is 1 plus this like 1 over here. And 6 is actually either 3 shifted or it's 2 with a 1 over here. And 7 is 3 with another 1 over here. And 8 is 0 with a 1 over here. So essentially, at every like number of 2, at every new number of 2, it's just going to be the old number plus the 1 like wherever you are. So let's look at that, right? So we're going to look at powers of 2. So this is 2 to the 0. And we are going to say not like, we're going to say like what's the lower bound here. So 0 is 2 to the 0, right? Let's actually, 2 to the 0 is actually 1 here. So I guess it's not entirely true. But essentially, we have to start with 0. So this is 2 to the 0. Okay, now this is 2 to the 1. Now 3 is still 2 to the 1, right? It's not quite 2 to the 2. Now we have a new power, 2 to the 2. This is 2 to the 2. And we're gonna look at the lower bound of the 2, and then 2 to the 3. Okay, there we go. So now essentially we have this. So we can make a default for 1, but we can also just say for 1, let's just take whatever is in 0 and let's add 1, 1 to make that 1. Right? But what about, so, but either way, you can make these default cases. You can just say, like, for 0 it's this, for 1 it's this, and that's going to make it a little bit easier to understand. So for 2, it's 2 to the 1. So what's the difference between that and 2 to the 0, basically? Well, it's literally just a shift, right? So if you look at this, like, this is the first value, that's 2 to the 1. So you could see, like, here and here, it's just one shift. And here, it's one shift, right? From 2 to the 1 to 2 to 2 is one shift. And then from 2 to the 2 and 2 to the 3, it's also one shift. And then what about some other values? Let's take a look at something else. So if you look at this section, and this is going to make it a little bit easier to understand as well. If you look at this section here, let's actually draw that in another color just to make it, like, more clear. This section right here, this 4, 5, 6, 7. Well, this is actually the same exact thing as this, right? Except here it's zeros and here it's ones. So that's the only thing that's changed. So these 4 numbers are the same as these 4 numbers, but you just add a 1 in the front. So if we know how many ones are in these first 4 numbers, then we know how many ones are in these numbers here. You just add 1 more, right? So from all these, it goes like that. And the reason is because, like, at 7, if you take a look, let's look at something like 7. So 7 right now we have 2 to the 2. So actually, if we just take the current power of 2, we're at a number, and subtract, and let's do that. So 7, we're going to subtract 2 to the 2, so we're going to subtract 4. We're going to go to 3. And you can see 7 is literally a 3 with another 1. Well, let's try that for another number. Let's try 6. So we subtract 2 to the 2, and that 6 is literally a 2 with another 1. Same thing, right? It's just however many numbers were in here plus 1. Let's try 5. Same thing, right? It's 1 with another 1. 4, 0 with 1, 1. 3 are 2 to the 1, so we would subtract 2 now. So you could see, like, if you just keep track of the power of 2 for every single number, this works, right? Like, this is 2 to the 0, and like I said, these we can default. These 2 we can default, and then everything else we can use. But yeah, essentially you can do the same thing, right? 2 to the 0 is actually 1, so you can say, like, how many ones are in 1? Well, it's whatever's in here plus 1, right? So that works, right? So the number of zeros in 1 is whatever's in here plus 1, and let's just go through the rest of it. And we can even add more numbers to make sure that works, and we'll do that in a second. So for 2, remember 2 to the 1 is 2, so we're literally saying, okay, there are however many numbers in here, how many number 1s plus 1, that works. 3 works. 4 works. So you can see that reoccurring pattern works all the time, right? Here, here, and here finally. It always works. Now let's try a few more numbers just to get it, like, really ingrained, and let's try it for those. So we're going to do 9, 10. There are going to be, like, a few more numbers here, but that's okay. 11, 12, 13, 14. And we're even going to try to make a shortcut. I don't know if this will work, but I am curious. So let's give it a go. So let's actually just say, let's just take this whole thing and let's just copy it, right? And we're going to paste it. Oh, it did work. Okay. So we are going to paste it here. And then we're going to actually move these numbers around a little bit. So let's actually delete some of this. And let's use this and let's match it up. So we can actually, I think we can just do this. There we go. Okay. So actually, if you notice what I did, I literally copied the first 3 digits for everything, right? And let's see if that works, right? So 13, 14. I think I may have copied too much. Let's see, 9, 10, 11, 12, 13, 14, 15, 16. So I should have actually just only copied, I think I copied too many. Yeah, I definitely did. So let me redo that. 1 second. So let's actually get rid of all of these and let's copy, so what we need to do is copy 0 to 7. So let's do that one more time. So we're going to actually copy like this. And you're going to see this pattern, right? So we literally copied all of these. We're going to put it here. Does this line up? Sort of. Yeah, it's close enough, I think. Okay. So you could see that I literally copied all of these values, and now all I have to do, so actually this 0 should be a 0. Now all I have to do is just put a 1. And that should, for some reason some of these are missing though, which is kind of weird, but yeah, so for 10 this should be this. For 11 should be this. For 12 it should be this. 13, 14, 15. So you can see literally these numbers here, let's actually draw this. Yeah, over here. Okay, there we go. So you can see like these numbers here, not quite there. These numbers here, and these numbers here are literally exactly all the same, right? The number of zeros in that is all the same. And then the only difference is now for 8 through 15, we have a 1 here because this represents 8, right? So it's just 8 plus 0. You can think of that. 8 plus 0, 8 plus 1, 8 plus 2, 8 plus 3, 8 plus 4, and so on, right? So the number of ones in all of these numbers are literally going to be the same as the number of ones in all of these corresponding ones, right? So this is 2 to the 3, 2 to the 3, and so on, right? 2 to the 3. All of these are 2 to the 3. So for like 15, we would just subtract 8, and it's literally the same number, plus 1. So you can see it works. 14, we would subtract 8, we'd go to 6, and so on. So we can write down this reoccurring pattern. So for a given number, let's get its power of 2, right? And we are going to like lower bound. And then the number of zeros in it is 1 plus whatever this array, let's call this result, of the number's index minus whatever that power of 2 was. So 2 to the whatever power of 2 that was. Right? So for example here, if our number is 15, we would say, okay, its power of 2 is 2 to the 3. Okay, so the number of ones are 1 plus the index of 2 to the power of 2. So this part is 8. And then it's going to be 15 minus 8. So we just go to 7. So 7 has 3 ones. So we're going to say 1 plus 3. And that's going to have 4. And if we actually look, it's this. Right? So this works for literally every single number. And then our base case can actually just be the 0. So all we have to do is just update our power of 2 every time we reach a new power of 2. That's literally all we have to do. Every time we reach a new power of 2, we have to update our power of 2. And then we just have to go back that number of digits. And then it's literally, if you think about it, right? So once again, if you go from 10 down to 2, it's literally the number that you're referring to. And then you're just adding this like most significant bit for the 8. For that one more bit. And that's pretty much all of it. But yeah, I definitely think it's not an easy problem. Nowhere close. This is like not very easy to recognize. So, you know, don't be discouraged if you couldn't find the O of n solution. I do think the log n solution is pretty straightforward. Just like chop down the number bitwise until you get 0. Like that one's pretty straightforward. But let's code up this one. To do this. There we go. So we're going to make a result array, right? So we're going to say, let's make a result array. And we're going to say, we don't even need to check for 0. We're just going to give it some numbers, right? So if n is, for example, 2, we need to, how many numbers do we need? We need 3, right? We need 0, 1, 2. So this is going to be that. Now we are going to keep track of the current power and the next power. And the reason is it's going to make it a little bit more efficient, because what you don't want to do is you don't want to do something like 2 to the cubed, and then you want to do 2 to the cubed again, right? So we're just going to store these powers. We're going to calculate them once, and then we're going to reuse the value. Because once these things get big, you don't want to do something like, you know, let's say you do like 1,000,000 minus like 2 to the 20th, and then you do 999 whatever minus 2 to the 20th, right? You don't want to keep doing this. So every time you calculate one of these, you want to be saving it. So we're going to do that. Okay, so we're going to say for I in range 1 to n plus 1, because we do have this, like this, the 0 is our default one, and n plus 1 is the last one, and remember it's exclusive. So so the current power is going to be the current power of 2, and the next power will be the next power of 2. So we start at 1, which is 2 to the 0, and then the next power of 2 will be 2 to the 1, and so on. So we're actually just going to keep those values saved. So we're going to say if I equals next power, right? If we've reached the new power of 2, then let's just update that. So we can say cur power next power, and then those are going to be equal to, so current power is going to be next power, and the next power is going to be next power times 2, right? We're just going to calculate them, and we're just going to calculate them once and then use them over and over and over to make efficient calculations. Because like I said, you don't want to do something to a big power of 2 50 times. You know, that's not going to be efficient. So, okay. And then dp, it's not going to be dp, it's going to be result I. And then we're just going to use the current power, right? So it's going to be dpi minus current power. Like I said, you literally just figure out what power of 2 you're on, go that many digits back, and then you add 1. Well, as in this picture, right? So you take index of 2 minus the current power of 2 you're on, plus 1. So that's literally what we're doing here. And then finally, we can return the result. This should be result, not DP. And let's give it a go. So you can see it's pretty efficient. And yeah, if you didn't use these values, if you just manually calculated the power of 2, I did try this before. It's significantly less efficient, as you can see in like some of these, I think. Okay, so yeah, that's going to be all for this problem, but let's do the time and space first. So now our solution is linear time, right? Because we're essentially looping through our numbers one at a time, and we are doing constant time operations. We're just getting the value, we're getting some old value, and then we're just calculating a next power when we need to, but that's not super often. We're calculating a new power like log n times or so, but either way, even if we did that every time, that would still be constant time, or n time. Now for the space, so we do have this result array, but we don't count for that, and then we just have these 2 powers, so it's going to be of 1 space because we only have the result. And yeah, it's going to be it for this problem. Hopefully you liked it. Like I said, definitely not an easy problem, so don't get discouraged if you didn't finish the linear time solution, because it's definitely not easy and not super intuitive. But yeah, hopefully you liked it, and thanks for watching. If you did like it, please like the video. It really helps grow the channel. And I think we're actually almost at 400 subs, so thank you guys for that. And I'll see you in the next one. Thanks for watching.